chi-square test comes with a limitation, though it is used for measuring the association when both your variables are categorical. So if we talk of Pearson correlation, so both the variables are continuous in nature. If one is ordinal, then and another one is continuous, then we use Kendall-Tau or Spearman interclass correlation. If one is continuous, another one is dichotomous, then we use biserial or quant-biserial correlation. But what if both of your variables are categorical? For that purpose, we use a test which is known as chi-square test of independence. So this test is used to measure the association between categorical variables, and it is basically a non-parametric test. So it is used to measure the statistical independence or association between two or more categorical variables. For example, I want to test association that whether smoking causes cancer or not. So in that case, I am having two categories, smokers and non-smokers. Another category is cancer and non-cancerous. So if I have to test the associations, I will be getting a 2x2 matrix, and that matrix will be let's say smoker, non-smoker, cancerous, non-cancerous. So there will be few people who will be smoker and having cancer. Some people who don't smoke, but still they have lung cancer by due to some different reasons. There will be people who are smoking, but they didn't have cancer. And there are people who are non-smokers and also they didn't have the cancer. So like this, we will get a contingency table or a cross tabulation. And then we will find out that what is the association between them. So let's say I'm putting some random numbers in like this. So this is the observed frequency. So the formula of chi-square is chi-square is equal to summation of O minus E square upon E, where O is the observed frequency, which we are getting these frequencies here are observed frequencies. This E is the expected frequency. And when you subtract the expected frequency from the observed frequency, take its square upon E and sum it all, we get the results of chi-square. Now, observed frequency we have got from where to get expected frequency. So this expected frequency is equal to row total into column total total upon grand total. Upon grand total. So our row total is 12 plus 10, 22, and 16 plus 15, that is the row total. Column total is again 10 plus 15, 12 and 16. Multiply this, then divide by the overall total frequency, you will get the expected frequency. Put it into the formula and you will get the chi-square, result of the chi-square. Here, the difference between O and E is also known as the residual of the cell. Degree of freedom in case of chi-square is equal to row minus 1 into column minus 1. So we have 2 rows and 2 columns. So 2 minus 1, 1, again 2 minus 1, 1, 1 into 1, 1. 1 will be the degree of freedom in this case. So this is how it is calculated. But one limitation it has, this chi-square has one main limitation, and that limitation is that minimum count for each of the cells that you are getting should be 5. If it is less than 5, then chi-square won't give you correct results. Even it won't be able to compute the statistics, chi-square statistics. So what to do in that case, that also I will be telling you. So first let's do a chi-square test in SPSS. Are you clear with the theory behind the chi-square? How it is calculated? Okay. Though it seems to be a very simple test, but it is very useful when you want to test the association between nominal. Most of the time in our questionnaire, we have many of the demographic variables. And then question arises that what should we do with the demographic variables? Simply telling about the let's say mean you cannot calculate, so frequency distribution would serve the purpose. It would be better if you find out some relationship between these categorical variables. Sometimes in our question we have multiple choice questions, multiple options. So again, categorical variables are there. So in that case also we can use this chi-square. But the only limitation, please keep in mind, minimum frequency for each of the cells should be 5. If it is less than 5 in any of the quadrant, in any of the cell, if the minimum frequency is less than 5, then chi-square statistics won't be computed. So let's do one chi-square test. So open the file, that sample data set. So here we have variable smoking, and also we have variable gender. We want to know, is there any relationship between gender and smoking? So you see, gender is again a nominal variable divided into 2 categories, 0 for female, 1 for male. And smoking is again a nominal variable divided into 3 categories, past smokers, 0 non-smokers, 1 past smokers, and 2 current smokers. And I want to know what will be the relationship. Is there any relationship between them? In this case, if you see the degree of freedom, we have, let's say, 3 categories of smoking. So degree of freedom will be 3 minus 1, and 2 categories of gender 2 minus 1. That will be 2 into 1 is equal to 2. So this is our degree of freedom in this case. At this degree of freedom, we have to check that whether is there any relationship between these two variables or not. So go to analyze descriptive statistics cross tags. Now here the assumption is that the main assumption that every cell will be having minimum 5 counts. If it is not having them, you should not run chi-square. In fact, chi-square won't give you these statistics also. Sometimes it is written after the table that I'll show you. It shows 80% of the cells have minimum count less than 5. So actually that is the error in your test. But if you are still doing means you are doing an erroneous test. So please bear in mind that this minimum frequency count should be, this assumption should be met. Now what we will do, we will put smoking in the row, gender in the column, and here in statistics, we will take this chi-square, continue. Also for visualization, we will take display clustered bar chart. Click on it. So please always remember one thing, that whatever you feel is a dependent variable should come in the row, and whatever you feel is an independent variable should come in the column. So smoking is dependent on gender or independent. That's why we call it as chi-square test of independence. Whether smoking is independent of the gender or not, that we are trying to make. So if you see here, the Pearson chi-square value, this value, it is coming to be 3.171 at the degree of freedom 2. I told you how to calculate the degree of freedom, but it is non-significant. P is greater than 0.05. This simply means there exists no association between gender and smoking, or smoking status is independent of gender. So chi-square is equal to 3.17, DF is equal to 2, P is greater than 0.04. So due to this, we can say yes, of course, I will discuss less than 5 cases in this example. So H0 will be, okay, you want me to write the H0 and H1, okay. So our H0 will be in this case, there is no significant association between gender and smoking. Or you can write this H0 like this also. smoking is independent of the gender, right? H1 will be smoking is dependent on gender, or there exists a significant association between smoking and gender. Since P is greater than 0.05, so we fail to reject the null hypothesis. So we have to say that, we have to interpret that there is no association between smoking and gender, or smoking is independent of the gender. Now, if you see your row and column, you are getting values more than 5 in every case. And here, if you see the results, 0 cells have expected count less than 5. The minimum expected count is 17.76, which is fulfilled. Okay. So I have seen people doing chi-square test where it is written that 80% cells have, or 70% or 50% cells have expected count less than 5. So if this is the case, your chi-square test is wrong. Okay. So it should be none of these cells should have expected count less than 5. Minimum 5 count should be in each of these cells. So please, whenever you have done this chi-square test, please see what is written here. In most of the cases I have found, it is written that some percent of cells have expected count less than 5. In that case, your chi-square statistic is wrong. So what to do in that case? I'll come to that. Let's look at the visualizations. So this cluster bar chart, if you see, this blue bar is for females, 0, 1 is for males, the green. If you see in the category of 0, that is non-smokers, number of males and females are nearby equal. If you see in the category of past smokers, 1, number of male and female are again are very close to the count. And if you see in the category of current smokers, again they are very close. So even cluster bar chart is showing you that there is no significant that the number of males and females in each category are close to each other. I mean, there exists no significant difference between the males and females when it comes to smoking status. There is no association between smoking and gender. Even if you see this count, okay, in smoking 149, 148. Here in this past smokers, 13, 24. Okay, second 31, 37. There is no much difference. And if little bit of difference is there, but that difference is not significant also. So you can say from overall these cross tables, these contingency tables, from this p-values, and from this bar chart, cluster bar chart, all these are suggesting that there exists no association between gender and smoking. And also the assumption of minimum 5 counts is met in this case. Now, what if you are not getting these 5 counts, right? Taking this data only because I don't have any data as of now, if having less than 5 counts. So only taking this data, what I'll do, you go to analyze. Suppose this assumption is not met. So you go to descriptive statistics, go to explore, take your dependent variable, not explore, analyze descriptive statistics, crosstabs itself. So smoking, your dependent variable here, your independent variable, gender in the column. In statistics, here you will get this lambda. Okay. If you have 2 normal, now I'm telling you the case where you are trying to make association between 2 nominal variables but the expected count is less than 5. Then you should use lambda rather than chi-square. So click on lambda, continue. So you will get these associations. However, since this data is not supporting it, so very less association. So normally it will tell you the degree of association and the significance level also. You can see it is non-significant in all the cases, and also these values are very less. So ideally, this lambda value should be till 0.2. It is considered as weak. From 0.2 to 0.4, means 20% to 40%, it is considered a moderate relationship, and above 40%, it is considered a strong relationship. So you can use lambda in this case. Okay. If you are trying to find association between two ordinal variables, so you can use two ordinal variables for chi-square, but again, this assumption of minimum 5 counts is not met. Okay, when both are ordinal. See, if your both variables are categorical, means either nominal or ordinal, and minimum 5 expected counts in each of the cell is met, then chi-square is good enough to test the association. If it is not met, then if both are nominal, then lambda. If both are ordinal, then again you can go for gamma. Here you will find an option gamma under ordinal if both are ordinal. If one is ordinal, another one is nominal, then also gamma. Okay. So both are nominal. Please keep in mind, both are nominal or both are ordinal, but expected count is 5 minimum in each of the cell, then chi-square. If both are nominal but expected count is less than 5, lambda. If both are ordinal, expected count is less than 5, then gamma. Okay. If one is ordinal, another one is nominal, then again gamma. So click here and okay. Now here you will get this gamma value. It's very weak correlation, also not significant. However, this gamma and this lambda, they are also used in one more purpose for testing the reliability of categorical measurements. Because we use Cronbach alpha for testing the reliability of scaled variables, but for categorical variable like demographic variable you have taken, most of the time you discard them. We don't test their reliability. But since it is again a measurement we are taking, we should test their reliability. And that reliability is tested through gamma or through lambda, depending on what kind of measurement you are. So Cronbach alpha is not the only measurement for reliability. And please, when you are using Cronbach alpha, don't mix your categorical variable and continuous variables for testing the reliability. Please don't do that. Right? Do separately for the scale variables and do separately for categorical variables. Categorical variable you can do through lambda or gamma. So the association, if it is greater than 0.6, means 60%. Okay, here in this case, for Cronbach alpha, it's 70% or 0.7 or more like that. Here in lambda and the gamma, above 0.4 is considered as a strong correlation. So if for categorical variable, if this value that you are getting is more than 0.4, then it is a strong relationship. If it is greater than 0.4, strong relationship, and also hence categorical measurements are reliable. Because overall the reliability is nothing. I'll come to the reliability aspect if time permits. Reliability is nothing but inter-item correlations, right? So is this understood? Yes, Ms. Khushbu, smoking is independent of gender and H0 will be H1 will be smoking is dependent of gender. There is no association independent of gender means no association dependent on gender, there will be association. Last point, okay. So I was saying that this lambda and gamma, apart from being used for testing the associations between the categorical variables. If they are ordinal, then gamma. If they are nominal, then lambda, provided that the assumption of minimum 5 counts in each cell is not met, then we should use this. Apart from this testing the association, they also give you the reliability. So I have said that reliability is nothing but correlation, inter-item correlation. Reliability is the measurement of inter-item correlation. So,
sir, this 0.4 thing was not clear, sir.
Okay. So what I am trying to say in case of lambda and gamma, till 0.2 or 20% is a weak correlation. 0.2 0.2 to 0.4 is considered as moderate correlation. Greater than 0.4 is considered as strong correlation. And the reliability is the measurement of correlation between items. So if it is greater than 0.4 means strong correlation. If this value is greater than 0.4, then that means there is a strong correlation, and you can say that your categorical measurements are reliable. Now is this clear?
Yes, sir.
Fine. So these are, apart from testing association, these are also used for testing the reliability. Because most often researchers have reached out to me asking, sir, that we have seen all the videos where they say that Cronbach alpha is used for testing the reliability. But what about categorical variables? What about those demographic variables, age, gender, income status? How to check whether they are reliable? So for that case, you should use this gamma or the lambda based on, and the value should be greater 0.4 or greater than that. I hope this is clear now.
Yes, sir.
Now this was all the test of associations. Now let's move on to the test predictive analytics. So predictive analytics, basically I'll talk of the regression. Quickly, can any one of you tell me the equation for regression? So we all know that outcome is equal to model plus error. Now using this, can any one of you tell me the regression equation? This is very old school of thought, y is equal to mx plus c. This is simple linear regression. So in this, outcome is y is equal to, in the model we put b0 plus bx. plus error, where B0 is the, what is B0?
Constant.
Apart from constant, any other name for it?
Y-intercept.
Intercept. What is B?
Slope or gradient.
Gradient or slope. Right. It is also known as the regression coefficient of variable x. So this is the case when you have only one predictor variable. So it is the case of simple linear regression. If you have more than one predictor variables, then y will be y is equal to b0 plus b1 x1 plus b2 x2 plus b3 x3 to bn xn plus error. What is this error? Can anyone of you tell me what is this error? See, none of the predictive model can be explained to a level of 100%. R square cannot be 1. So whatever has gone unexplained is due to these residual errors. And what they look like, I'll show you. Because if we are talking of linearity, that means we are fitting data on a straight line. So this is our straight line. Okay. So data points that are lying apart from these straight lines are known as residual errors. Right? And the model cannot be explained to 100% level. So whatever has been gone unexplained is due to these residual errors. So, but they also needs to be accounted in the equation. So if the data points are lying above this vertical line, then they are known as positive residuals. If they are lying below this line, then they are known as negative residuals, and they overall affect the model performance. So if you have many residual errors, means many of the data points not fitting on this straight line, your model would not be a good fit, or the level of prediction will be very less. So you have to see in this case that what variable you should choose. So first thing that you should minimize the residual errors and be very cautious about your variables. So this was the residual error. And the B0, why we factor in B0 in this formula? Because B0 is a value which can predict even if x is 0, then also y can be predicted with the help of the constant. Because if we don't put this here, if you strike off from here, if x is equal to 0, then y will be 0. How will we predict y? So let's say if the value of x is 0, then this constant or this b0 or this intercept helps you to predict y. That is the importance of this b0 or the intercept. Okay. And Now, there are few assumptions for regression that needs to be made. So first is assumptions of a regression. Linearity means linear association between the variables dv and iv. Second is no auto correlation. It is tested by Durbin-Watson statistics. No multicollinearity tested by tolerance value TV variance inflation factor VIF. Fourth one is here we check not the normality of the data but normality of residual errors tested by normal PP probability plots or Anderson Darling test available in RM Python. So in SPSS we test by normal PP plots, probability plots. So here in this case, Durbin-Watson statistics should be between 0 to 4, where TV should be greater than 0.2, VIF should be less than 10. If VIF is between 1 to 5, no problem of multicollinearity. Between 5 to 9, some problem of multicollinearity. Greater than or equal to 10, serious problem of multicollinearity. These are the cutoff values. Tolerance value should be greater than 0.2 and VIF should be less than 10. If it is between 1 to 5, then very good. In normal PP plots, data points should be lying close to the diagonal line and should be in symmetry. Okay, so these are the requirements for doing a regression. If any of these are violated, then you have a serious problem in the model. Particularly this multicollinearity. Why this is a thing which is of importance? Let's say a case where you have variables x1, x2, and x3. Now this x2 is actually not explaining y. It is not contributing to prediction of y. But it is in your model, it is predicting because it has high correlation with x3. x2 is highly correlated. Multicollinearity means that there is a high correlation between the independent variables. So there should not be multicollinearity. Why it should not be? Let's say x2 is highly correlated with x3. If it is highly correlated with x3, it is borrowing its attribute from x3. Actually, it is a non-predictor of y, but it is showing some prediction on y because it has borrowed some of the characteristics from x3. So in that case, due to the high correlation, in that case, your model is not a good fit. You are saying that y can be predicted by x1, x2, and x3, but in actuality, x2 is not contributing to y. So to ensure this, to weed out those variables which are not actually explaining your model, you should do the multicollinearity test. There should not be multicollinearity. That's very important. Normality of residual errors is also important because if data points are not in symmetry, they are not close to the to the diagonal line, means they are moving away from the diagonal line. That means a lot of residual errors are there. And lot of residual errors will lead to less explanation of the model, making it a bad model. If you are taking a time series data, there should not be autocorrelation between the variables. If it is there, then again it's a problem. It's the same problem like multiple. And of course, the basic requirement, since it's a linear regression, there should be a linear association between the variables, and that we test by scatter plots. So these are the assumptions and these are the tests, how they are tested. Is that clear? See, autocorrelation is again the correlation between the variables, particularly in a time series data. We have to have, there should not be any kind of correlation between the variables. Your independent variables should not be correlated with each other. Is that clear? No. I'm not saying no correlation between X and Y. You have to test correlation between X1, X2, X3 if you have many independent variables. There should not be correlation between independent variables. Y is apart from this. We are not testing any correlation. See, if X and Y are not correlated, then you cannot predict Y based on X. There will be some correlation between X and Y, but there should not be strong correlation between all your independent variables. All these assumptions, except the linearity assumption, the rest three assumptions, this autocorrelation and multicollinearity assumptions are applicable when you are doing multiple regression. Means if you are having more than one predictor variable, more than one X, then they should not be correlated with each other. Is that clear? So in multiple regression, see, linear.
But then how autocorrelation and multicollinearity, these two concepts are different because both of them say that independent variables should not be related to each other.
So this autocorrelation, actually, this applies basically to the time series data.
So that is okay, but then what is the difference between 2 and 3? Both of them point towards correlation between independent variables.
That's what I'm saying. This autocorrelation happens between the data when you are taking a time series data or when you are doing this longitudinal study, when you are doing a cross-sectional study, right? At the same point of time, many variables, then we check basically for multicollinearity.
Okay, sir. Okay, got it, sir.
Okay, so somebody has given this example. So for 100-year rainfall data from them, there should be no relationship between rainfall of 1902, 1903, 1904, etc. Yes, then only you can predict. Otherwise, if there will be, I'm not saying, see, again, you people are confusing. There can be little bit of correlation, but not high correlation. Okay. So multicollinearity says that there could be correlation, but not high. But in time series data, if you are taking over a period of time, at least there should not be correlation at all. Is that clear?
Yes, sir.
So when you are doing this cross-sectional study, many variable at one point of time, check for multicollinearity. When you are taking a time series data, check both for multicollinearity and autocorrelation. However, it's always a better idea to test both, that autocorrelation and multicollinearity doesn't exist. This is applicable only for when you have many predictor variables, right? When you are having only one predictor variable, then only linearity and normality of residual errors. Means when you are doing simple linear regression. When you are doing multiple linear regression, then all these four assumptions need to be. Is that clear?
Yes, sir. Very clear.
Okay. Now let's do it. So open this file album sales.sav. So in this, we have four variables. AdWords, which is I'll show you here. Advertising budget. So every unit is in thousands of pounds. So this means 10.26 into 1,000 pounds. Okay. Then album sales in thousands. This is the sales. Airplay means number of times a music album was played on the radio, and attract means the attractiveness or the popularity of the band on a scale of 10, which made the music album. So there is a data of 200 albums, music albums, right? And based on this, the music company owner, he wants to predict the album sales based on advertising spends, their advertising budget, number of times the music album is played on a radio, that is airplay, and attractiveness of the band that created the music album on a scale of 10. How all these will be able to predict the sales of the album. Is the problem statement clear?
Yes, sir.
So just let me check. KB man, is there a break? Should I continue? Okay. Once it is there, please let me know. Okay. So based on this, he wants to predict. Now, the thing is that we know whenever we do regression, we should be very particular about what variables we are choosing to predict. We should choose your predictor variables very carefully. Why? Because see, when you are doing a study, you'll find that there might be many variables which are affecting the outcome. But few will be relevant, few will not be that relevant. So why to take those which are non-relevant? Because ultimately adding more and more variables in the model will spoil the entire model. So you should be very careful. And how? Again, in every session I'm I'm emphasizing on one thing, literature review. The variables that you will choose should come from a very strong grounded theory. It should not be a thought of your own mind or some XYZ study has published once in a while and you are saying, no, would also be a predictor variable. Choose predictor variables which are really very relevant. Otherwise, they will underfit or overfit your model. So let's say in our case, we know advertising a budget can directly affect the sales. Yes, number of times the song is played on a radio, the music album is played on a radio more number of times, people will come to know more about it. This can also affect the sales. Attractiveness of the band. If the band is very popular, of course, people will go for buying the music album created by those bands. But here, will the cost of production also affect the sales? Let's say I want to factor in one more variable, cost of producing the album. Will it affect the sales? Should we take this variable into account or not? Anyone?
Not really, sir.
Directly it won't, because me as a customer is least concerned about what was the cost of production. However, cost of production might increase the cost of the price of the album, which can decrease the sales. But what if the music album owner keeps less profit margin? So this could be one variable which is affecting. I'm not saying it is not affecting, but compared to these three, it is not that much important that you should take into account. What I mean to say. If many studies are saying, then fine enough, you can take it. But in my opinion, if I have to factor the cost of production, I won't go further because that won't directly affect the sales. So why to put more variables in the model? The more you put the variables in the model, there are fair chances that your model will be the underfit or the overfit. Also, if any model is not, any of the variable is unable to explain, chances are that it might be dropped out of. So this is the first thing. Apart from assumptions, you should keep in mind while doing regression. Second thing is that choosing the method of regression, which we normally skip, particularly in multiple regression. First, I will show you one first assumption, linearity, how to do it through scatter plots. So go to the graph, go to legacy dialogs, and you will find here scatter dot. Select simple scatter, define. What is our Y? Album sales, advertising budget I am taking. Okay. I got the scatter dot, double click on it and draw a diagonal line at fit line and total. You'll find that there is a linear association between the variables. Then second one, similarly you take now number of plays on radio. And one thing you might be noticing that the regression coefficient of the relationship also is given here. When you will do in the model, you will find it. Right here also. So here individually you can say that there is a linear association plus this advertising budget is able to predict album sales to a level of 33.5%. Similarly, there is a linear association between number of plays on radios and album sales. And number of plays on radio is able to predict the album sales to the level of 35.9%. So individual regression coefficient also you will get. However, when you will do it, put all in a model, then you'll find that the regression coefficient will be different. This is the regression coefficient when individual variable is predicting the sales. Then go to the third one. Select this. And take attractiveness of it. Here there are more residual errors. If you see, very less are fitting to the line. There are more residual errors. Why R square value is not coming. So there are more residual errors, so R square is not computed in this case. So individually, you can say that attractiveness of the band is unable to predict album sales. But when put into the model, we'll see that how it is affecting. But individually, it is not affecting. Is that clear? Is that clear to you?
Yes, sir.
Right. So first assumption.
Then, sir, because two variables are only linearly associated, attractiveness of the band is not associated. Shouldn't we remove it before going for regression?
See, based on only one thing, we should not remove. See, when put together, we'll see that how it is affecting, right?
Okay, but the first condition is not fully satisfied. That is why I'm asking why is it so?
First condition is not fully satisfied. One of the variable is not having linear association, and R square cannot be computed. But since this is one of the variable of our interest, we will see that in the model, if it won't explain, then automatically it will be dropped. Okay.
Yes, sir.
So other two are, see, little bit of this. If all three out of these three, two are are in linear association, and we want to keep this one also, we'll see that how it affects in presence of these two. Individually, it is unable to predict. Okay. And I'm not saying, I'm not saying that there is no linear association. There is some data points are lying on this line, but most of them are residual errors. If you see, most of the data points are far below and above this line. Only few are fitting to the straight line. So little bit of linearity is there. I'm not saying that it's completely detrended. There is little bit of linearity, but it is unable when it is put singly to predict the album sales, then it is unable to predict that. Okay, but we'll see that in presence of other two variables, how it is affecting, how it is predicted, right?
Yes, sir.
Are you getting my point? Now we are seeing first linear association. This is having many residual errors. That's why the R square could not be computed. So it is a clear indicator that attractiveness of the band alone cannot predict album sales, while number of plays on radios alone can predict album sales to a level of 35.9%, and advertising budget alone can predict album sales to a level of 33.5%. But when put together in the model, we will check that how this relationship is changing, right? This is the initial overview that you are getting, that individually which of the variable could explain, right?
Yes, sir.
Now, so go to analyze, regression, linear. If you have one variable, then okay. If you have many variable, now album sales independent. So now you have seen, see here there is a method of regression, right? So enter method is a forced entry method. Means I will put all these three at once and let the software decide, because when regression happens, it happens first variable one will be regressed with album sales, then variable two, then variable three. When we are doing forced entry, the enter method, this is also known as forced entry. What it will do, it will choose the first it will choose that variable which is explaining the album sales to maximum, right? Then it will choose, let's say, variable three, variable two is able to explain the album sales to the level of 60%. So first it will take variable two. Then it will search for remaining 40%. Let's say advertising budget is explaining this remaining 30%. So it will take advertising budget. Then search for the third. If 10% remaining, if attractiveness of the brand is explaining in the model, attractiveness of the brand will be put at the third place. Or if two variables are able to explain to the level of 100%, then it will drop the third variable, right? Though it is of your interest, but it is dropping. It is a similar situation that because this is a software, you are putting in some numbers, based on some numbers, it will give you some more. Why this enter method is a problem? See, you should use this enter method when you are not very sure that which of the variable will explain to what level of the outcome value. If you are not sure that how much they will explain, which of them is the most relevant, then you put all three or four, how many you have at once. Do forcing. But in this situation, you are letting the software to choose which of the variables should be regressed first. It is the similar situation that there is a winter outside, cold weather outside. You have your jackets, shirts, trousers, and undergarments to wear. Now, if you ask this software that what should I wear first so that I could be protected from cold, so what it will suggest you? What it will suggest you? Any answer? You have a jacket, your shirt, trousers, and undergarments. There is a cold outside. You are asking the software that suggests me what should I wear first. Build a predictive model for me that what should I wear first so that I should maximum get protection from cold. Jacket, of course. So it will ask you first wear jacket, then wear your trouser over that, then wear your shirt and trousers over that, then wear undergarments. Ultimately, you'll be protected from cold. But will this be a good model fit? First wearing jacket? No. So it's the same problem with forced entry. Unless you are completely unsure, completely blank that which of the variable will be explaining maximum, then you can do forced entry. Otherwise, do stepwise. Okay. In stepwise, we first choose the variable which we believe that they are maximum explaining the variance of our outcome variable. And then in the next stepwise, we do this. Based on this, we have the remove method that we keep on adding and removing the variables backward, forward, all this. So unless you are unsure completely, please avoid this center method. Because I have given you one example how it could affect your model. Overall, your model will be explained, but the fit won't be good. It will be a bad fit. So now can we take a 10 minutes break, and after that we'll resume the session? Is that okay? So now we resume the session. Am I audible? This audience, am I audible? Since audience have gone on a break.
Yes, sir. Audible, sir.
Okay, okay. Fine. So let's move forward. So here I have taken this album sales, a dependent variable. From our scatter plot, we have come to know that advertising budget is explaining this album sales to a level of 33.5%. And number of plays on the radio, it was explaining to a level of 30, to a level of around 39%. So we are clear about this. We are not sure how attractiveness of the band will be. So rather than force entry, I will do a stepwise entry. So in the first step, these two variables, because scatter plot has told me that they are explaining the album sales, and then go to the next. This is also known as hierarchical regression. So if you hear something like hierarchical regression, don't get confused. Hierarchical regression is nothing, this multiple regression done by using the stepwise method, right? Then in this second step, I will add attractiveness of the band. Similarly, if I have the fourth one, which I am not sure how it will affect, I'll put it in the next step. So like this, you can keep on adding. Okay. So if you see in the first step, advertising budget and number of plays, because they both have shown during this scatter plot that they are associated with predicting album sales. Attractiveness of the band, we are not sure about, but this is one of the variable of interest. So we will put it in the end. Similarly, in the order of the explanation of variable or your surety, you can put these variables in by clicking next in stepwise method or hierarchical regression, rather than forced entry, because where the forced entry will pose the problem, I already told you. Now coming to the statistics, we want estimates, model fit. Since we are doing hierarchical regression, so we also want R square change. In the first model, when we regressed with the advertisement and number of plays, what was the R square? And in presence of attractiveness of the band, when we added to the model, whether R square increased or decreased, that will help us to decide whether to keep the first model or the second model. So R square changed. This autocorrelation of residuals, normally it's a problem in time series data, but here also we are predicting the future. So the present value and the future value should not be correlated. For that, for the sake of that, we will put Durbin Watson for multicollinearity. Then here collinearity diagnostics. Sorry, this for autocorrelation and collinearity diagnostic for multicollinearity. So here you have to click estimates is by default clicked. Model fit is by default clicked. If you are doing hierarchical regression, R square change. For multicollinearity, collinearity diagnostics, and for autocorrelation, Durbin Watson. Continue. In plots, here we will plot Z score of the residuals with standardized score of the residuals for getting the normal PP plot. Okay, for testing the normality of residual errors. So this versus this, click on histogram, normal probability. Continue. Save option. If you want to save the variables in standardized and the predicted values in in standardized form and unstandardized form, click it. If you want to save the values, means whatever the regression equation you will get, after that regression equation for each value, how much will be the album sales, if you want the predicted values, if you want to keep, so automatically it will put into the formula and calculate. In options, nothing needs to be done, everything is okay. Fine. Run this regression. Now the first thing that you will see that how many variables were entered. So all three were entered. Now coming to the model summary. There is some R square change value also. There none of the variables were removed. So see the value of R square. In the first model, when only album sales was regressed, so it has given 35.9. It was able to explain, because we report this R square, it was able to explain the album sales to a level of 35.9% alone. And you can see also the first one, it has regressed actually with number of plays on the radio in the first model. Then in the second model, when number of plays on the radio along with advertising budget was regressed, then variance explained reached to 62.9%. Then when we added the attractiveness of the band also, you can see in the first model, it has taken number of plays on the radio and 35.9% was predicted alone by number of plays on the radio. And you can see here, if you see the number of plays on the radio, when we draw the scatter plot, exactly 35.9% alone by number of plays on the radio. But when in this model, advertising budget was also added, the variance explained reached to the level of 62.9%. Then again, album sales alone, it was unable to predict the attractiveness of the band alone, it was unable to predict the album sales. But in presence of these two, when it was added, now the overall variance explained reached to the level of 66.5%. So which model we should keep with us?
The third one.
The third one means when all variables are there, right? So now this tells us that the predictive model that we have got, this is explaining. So I'll just write the interpretations here. (66.5% variance explained). Means put together into our regression equation, these three variables will be able to predict the album sales to a level of 66.5%. The remaining 33.5% which goes unexplained is due to residual errors. Unexplained is due to residual errors. However, 66.5% is not a bad mark. So 66.5% is good. Variance is explained. There might be some other variables which we have not included or residual errors. Now, there is also adjusted square. What is this adjusted R square? Any idea? Most of the people are confused whether we should report R square or adjusted R square. So let me make one thing clear, that you should report only R square for variance explained. Adjusted R square is used for cross validation of the model. Cross validation of model. And this R is the correlation. So you see the correlation also increased to 81.5% between Y and all these three X, right? However, let's focus on this R square and adjusted R square. So adjusted R square is used for cross validating the model, that because we got this model on a sample of 200, whether this model will be able to predict in the population. Whether can we use this model? Because whenever we are making a predictive model, our aim is to make prediction model from the sample and generalize it to the population. So if there is no much difference between R square and adjusted R square, here you can see 0.005 is the difference. If there is no much difference between R square and adjusted R square, the model is cross-validated. It is able to predict in the population. Means the model that you are taking, it can be generalized to the population. This is the role of adjusted R square. Fine. Then this Durbin-Watson is ranging between 0 and 4. No autocorrelation. So first assumption of statistics of regression, linearity, we have checked. Second, no autocorrelation is also there. However, this is we should check basically in the time series data, but here because we are predicting the future, so we are keeping it. Now, what is the role of Anova here? We haven't given any command of Anova, but it is calculating Anova. So what is the role of Anova? This tells you about the fitness of the model. So adjusted R square tells you about the generalizability of the model, and Anova tells you about the fitness of the model. So for the model to be fit, F value should be greater than 1. The Friedman value should be F value should be greater than 1 and significant. Means P should be less than 0.05 for a model to be fit. So here you see the F value is 129.5, which is far above from 1 also and significant also. Means the model is a good fit. So till now we have come to know that the model is generalizable, model is the good fit. Also, the model can explain to the album sales to a level of 66.5%. Now, what exactly is the model? We are talking of model. What is this model is? So model is here to put these things into equation. So the equation was y is equal to, where Y is the album sales, albums. Album sales Y is equal to B0 plus B1 X1 plus B2 X2 plus B3 X3. Now put the value of B0 from this table. So the third model we have taken. So what is the value of B0 here? Anyone? This is our no, this is not B0. Our B0 is this constant minus 26.613 plus B1, the regression coefficient of variable 1, 3.367 into number of plays on radio. Plus B2, advertising budget 0.085 into advertising budget plus B3 11.086 into attractiveness. So in this model, you put the value of number of plays on radio, the advertising budget, and attractiveness of the band. You will get how many albums will be sold. Now, if you are a consultant to this company, what you will suggest, what they should do to increase the album sales? See, if this song is played one more time on the radio, 3,367 albums are sold because the unit is in thousands. So 3,367 albums sold. If they spend one more unit of, if they increase their advertising budget by 1 unit, the album sales will increase by 0.085. Means if advertising budget is increased by £1,000, because again it is in £1,000, 850 albums will be sold. If attractiveness is increased by 1 point, means let's say if the album was created by a band which has the popularity of 7 on a 10-point scale, now another album is being made by a band whose popularity is 8, then the album sold will be 11,086. So one more time song music album is played on the radio is yielding 3,367 albums. One more time advertising budget, one more unit means 1,000. For 1,000 pounds spent, 850 albums are sold. Attractiveness, the band which is creating the album, if their attractiveness is increasing by 1 point, 11,086 albums are sold. So which one is the better option? Out of these, of course, all these three will explain album sales, will predict album sales. But out of these three, on which the album company owner should focus?
It can increase the attractiveness of the band because it can ask that band to play those songs so that the sales increase, because this has the highest impact on sales.
Khushbu is very close to the answer. See, attractiveness of the band will of course lead to 11,036 album. It is the best solution, but in statistics we always, or in business problem, we always try to find the optimal solution. So suppose if the responsibility of increasing the popularity of the band is on the music album owner, company owner, then he has to go for lot of promotions, lot of concerts. That will incur huge cost to him. Again, it will be added to advertising budget, okay, nothing else. Suppose if album already is very popular, and of course she is very close, attractiveness of the band is a long-term game. It will take a lot of time for the band to become attractive. Let's say that the band is already established brand name and it is attractive. Don't you feel for making the album it will charge very high? Advertising budget is least contributing. But only one more time the song is played on the radio is yielding 3,367 albums. So the optimal solution is this, because it won't cost much for playing one more time the song on the radio, but in return it will yield 3,367 albums. Is that clear?
So why are we multiplying this factor by 1,000? It is 3.367, but you're saying for 1 unit of number of, for 1 unit of played on radio, it is increased by 3,367 times. No, variable is not in thousands. Number of plays on the radio is.
When I was explaining the variable, have you heard it properly?
Yes, sir. But number of plays on radio is constant. There is no bracket, so we are not doing it in thousands.
No, only one time. I am saying on a scale of 10. I am not saying in 1,000. Attractiveness only one time. From scale of 7 to 8, let's say it's increased. Then album sale will be 11,086. Because this album sale is in 1,000. The unit is in thousands, right?
Okay. Album sales is in 1,000. Yes, sir.
No. See, advertising budget and album sales are in thousands of pounds. Other are in single units.
Yes, sir.
Now got it?
Yes, sir.
So it is on a scale of 10 only. Let's say from 7 to 8, if it is increasing, then 11,086 albums are sold. Advertising budget, 1 unit means 1,000 pounds. So if 1,000 pounds are spent, then 850 albums are sold. If one more time the song is played on the radio, 3,367 albums are sold. Now it is clear?
Yes, sir.
Okay, fine. So the optimal solution is this, which I would suggest. I'm not saying everybody should suggest the same. Depends on how much company can afford. But if I have to suggest, I will suggest that means only one more time playing on the radio won't cost much to the music album owner and 3,367 albums. So this is our overall model. Model is fit due to Anova. F is greater than 1, significant. Model is cross-validated also, means it can be generalized in the population. This model we can use universally for that music album company in future also, because if the model is not generalizable, it is not futuristic. The prediction is not proper. Whenever you are getting the much difference between R square and adjusted R square, please check your variable, please check your data. Now coming to the assumptions. So linearity, we already checked. No autocorrelation, Durbin-Watson. Now coming to the multicollinearity. So if you see, tolerance value should be greater than 0.2. In all 3 cases, you can see it is greater than 0.2. VIF should be less than 10. Between 1 to 5, it's highly desirable. We have 1.043, 1.015, and 1.03. Very good VIF value. So there is no problem of multicollinearity in our data. Now coming to the normality of residual errors. So if you see through the histogram also, right, they are normally distributed. If you see through normal PP plots also, you can find that they are close to the, means they are almost all are close to the diagonal line and are in symmetry through normal PP plots. So all assumptions are met. Model is a good fit. Model is generalizable, and model can explain the album sales to a level of 66.5%. So this is all about regression. I hope it is clear. Yeah, if I play one time, sales increases by 1,000 because album sales is in 1,000 of units. One unit is equal to 1,000. Any query pertaining to regression? So if no query, then I'll wind up this session, and the remaining exploratory factor analysis, principal component analysis will be taken by our HOD by tomorrow at the same time. In the meantime, I am sharing my mail ID and calling and WhatsApp number. For any personal help, you can reach out to me on this number or this. I hope in the past 3 days, you might have learned something, some takeaway might be there for you. So we'll be taking a formal feedback by tomorrow. But if you wish, you can give informal feedback